everyone. This is the How to Build a CI from the Ground Up workshop session presentation. It's going to look like this. We are going to start from physical hardware topics, network, infra hosts, and then we are going to go through virtualization related stuff up until CI features, functionalities, logic. And then at the very end, we are going to have a Q&A sessions. One of my colleagues will drop in a Slido link into the chat now, so you can start collecting questions as we go through the presentation part. And you can also vote onto each other's questions. And at the end, we will try to answer all of them. But if we won't be able to answer all of them, then we are going to start with the most interesting questions based on the votes. We will roughly take around 60 minutes for the presentation part, and we will have like 30 minutes if everything goes well for a Q&A. Very quickly, who we are. Peter here, wow, he is tech lead for build infrastructure. He's going to talk about networking and build infrastructure hosts. Péter Vaskó Nagy is staff engineer at Bitrise. He's currently in the build services team. They are the ones who are building software on top of physical infrastructure. And I'm Szabolcs Gelencsér Szabi. I'm tech lead for Bitrise platform here at Bitrise. So I'm passing it over to Paul.
Hello, everyone. I'm Peter. I'm the tech lead of infrastructure, and I'm going to talk about the physical part of the CI/CD solution that we have. We have an on-prem solution, and networking in on-prem is the most important thing, is the foundation of everything. If you have any kind of instability here, you will break every other layer. So observability is a must, but don't just observe lost packets, because that will mislead you. Have end-to-end testing and deep understanding of what's happening in your infrastructure, in your networking, and have some nice SLAs, SLIs, SLOs, and measure everything that you can and make sense. And you will, when planning a network on-prem, you will need to plan ahead. Even before you do any kind of deployment, you do anything, and you have a rough idea of what you are going to do, what's your first size of the network, how many nodes, etc. Think about expansion. It is very important to know when is the trigger point of expansion, how that would look like, how much it would cost, because it will change your network layout and topology and how you choose your technologies. And also, don't forget what you need to support. Do you need good segregation of tenants? You need good separation of functions, deep buffers, etc. You need to be very thorough in your planning. But let's do a speed run of data center networking. How does it look like end-to-end? How the internet reaches us, how we reach the internet, and also I'm going to show you high-level data center networking, how it looks like for us, and how a good scalable pattern might look like for you. So first of all, let's start from the humble build machine. This is where CI/CD runs. This is where your npm install happens, or your customer's npm install happens. And the build machines are really simple things. It knows its IP and subnet, obviously, DNS, and where to reach the default gateway. This is obviously a simplified example because I'm ignoring the hypervisor. Hypervisor might introduce some extra layers here, but for our example here, this is the most basic thing. It knows where to reach the internet. And it will reach the internet through firewalls or gateways. These do network address translation and provide access to the internet for our customers and for our services. And for us, this is a homegrown solution. It might be different for you. For us, we needed more than what our previous vendor could give us at a reasonable cost. So we went ahead and created our own homegrown solution with commodity hardware. This solution is based on Linux. It uses keep alive the and what you would expect, but it has some extra um, magic in it, let's call it that. It is multi-primary, so if you have n nodes, then you have n active nodes, and you don't lose any kind of throughput because of active passive, which is good for handling peaks. And yeah, it's opinionated, but this is what we like, and we are fine with its drawbacks as well. And because this is we made it multi-primary, and we designed it to be not one-to-one, one active, one passive. It is extremely resilient and scalable, so you have you can have many nodes of this. Okay, the net gateways can send the traffic to somewhere, but the internet routers are the network devices that provide you access to the actual internet. We connect to the internet through tier 1 transit carriers. This can be solved with different approaches. You can peer with some company. You can have a connection to an internet exchange or many other ways. You can have most data centers provide you with a blended network, and that might be fine for you. It can bring you to a very nice level just having that. But for us, we needed tier 1 transit carriers. And obviously, if you are talking with the internet, you are using BGP. So we use BGP to advertise our IP ranges to the internet. And very importantly, this is a redundant pair. If you have a redundant pair and you have route diversity, you also unlock other things. For example, for us, we connect to two transit carriers. The two transit carriers see the internet differently, so we can route A traffic to one and B traffic to the other one at all times when they are both up, which means we can do um, uh, not traffic shaping, smart routing, let's call it that. Cool. And public internet. Why does anybody accept our traffic? So there are regional internet registries such as ERIN, which is operating in North America. There are as many regional internet registries as continents, basically. There is one for Europe, one for Africa, and so on. Here you can have a autonomous system number. This is basically your name on the internet, let's call it that. And this lets you talk with other autonomous systems, such as, I don't know, Google has multiple autonomous systems, and every transit carrier has their own. And you can advertise your IP prefixes. This is registered through the regional internet registries, but nowadays you can mostly just buy them through third-party resellers, because the IPv4 ranges were all sold out. So you have to buy it from somewhere, or you can also rent it. And once you have all of these, and you know all of these, you can put it up in the routing assets database, or ADB. Everybody does that. Google does that. AWS and everybody else does that. And this is the most important routing database. And it's fairly cheap to advertise your information there. Okay, we have all of these, but what about switches? For switches, we use EVPN VXLAN. This is an open source or open standards based solution. Basically, you could implement it yourself if you read all the RFCs. In EVPN VXLAN, the recommended at best deployment model is the spine leaf architecture. I will talk about it a little bit later. The great thing about eBPM and VXLAN is that this fits very well into our vision. We like resilient and high throughput solutions. With EVP and VXLAN, you can have multipathing, and with multipathing, you can have resiliency and high throughput, meaning unlike in old school networking with spanning tree, you can have resiliency with two active connections from one part of your network to the other part of your network, basically. And there is ASI lag. Basically, if you are familiar with multi-chassis lag, it's that, but with EVP and VXLAN. So you can have multi-homed devices. No single device has to depend on a single switch. Therefore, you can have very nice resiliency once again. And yeah, what EVP and VXLAN provides, and is very important, is it provides very nice segregation or segmentation of your network. You can separate your tenants, and you can divide up your network very securely. So let's go ahead and review spine leaf architecture. This is the most simple way to showcase it. You have two spines. Each of those spines is connected to all of the leaf switches. The interesting bit here is that no spines are interconnected. You might have, in some cases, leaf switches connected. Let's ignore that solution and opportunity for now. But the most important thing is that spines are connected to leaf switches. This provides us with a very nice and somewhat obvious scaling opportunity. You can have multiple spines or more than two spines. In most cases, you can easily deploy leaf switches with 8 spines, which means 8 times the throughput, which is super good. If you need that, usually you are good with 2 to 3. The interesting bit here is that every end device is connected to leaf switches, including our transit carriers. So our transit carriers are connected to leaf switches as well. This is the interesting bit here, where I said internet routers, what in reality, that is in reality switches which are acting as internet routers. This is super handy because you can have a border leaf or service edge, or however you want to call it. Basically, leaf switches which are connected to the internet. You can put your firewalls there, you can put your internet-facing services there, and you will have very nice performance because you can connect to multiple leaf switches from your endpoints. You can have redundancy, and it's super, super convenient. Yes, I believe I'm done with networking, and let's go to infra hosts. So once we have networking, we can connect things to it. But what do we want to connect here? And how can we beat hyperscalers? How can we deploy on-prem something that is competitive against Google, AWS, and Azure? First of all, hyperscalers love being generalized and generic hardware configurations. So that means that it can sell services to you, your competitor, and 50 million other companies. And yes, you can have multiple options, but these will always have these nodes that they use will always have a bunch of extra that is unutilized in 90% of the use cases. So know your own workload. And if you know your own workload, you will have multiple types of workloads. But if you know your workloads, you can optimize for it. And if you start ruthlessly optimizing, you can discover parts where, oh yeah, I don't need uh, network storage, or I don't need this function or that function, or other bits where you can shed some resiliency, for example. And with that, you can simplify your solution and you can spend the saved money on something that really matters and scales your workloads. And as I had said, know your workload and you can know where you can spend a little bit more. So as a CI/CD company, we have Linux for Android-based workflows and builds and etc. This is optimized for our the Linux hosts are optimized for our CI/CD use cases. For example, as I've said, we don't need network storage, we don't need network block devices and file systems over the network, etc., because that's not useful for us. So you can optimize just for local storage. And this is what we did. We optimized for it. And we can have a local storage that is faster than anything that you could get in a cloud vendor. Or we optimize for 4 to 16 core VMs, we can go up to 48. But if you know your scaling and what type of VM sizes you need, you can look in the CPU layout and you can look into the CPU architecture. You can buy a more cost-effective solution for you. And cost-effective might mean that it's much more expensive, but it's much more worth it. And much more expensive per CPU, but overall much more worth it. And with Linux, there are multiple hardware vendors, and these vendors are competing. So if you look at solutions and services and everything that they provide, one of them is out-of-band management on in all cases. HP, Dell, Supermicro, everybody provides out-of-band management. And this is amazing, and this is great because you can automate remotely. Uh, this is not news for those that run on-prem stuff, and this was not news for us either, but this is very important. If you are wishing to leave the cloud, this is something you have to research, and will make your life way easier if you know good solutions for it. And automations, because of this, is not hard because you have very good out-of-band management. But Linux is easy. Where it gets more complicated is iOS and macOS CI/CD. With M2, this is where we started our on-prem adventure. With M2, you don't have out-of-band management, and you have to do something because otherwise it's going to get very expensive with the remote hands and just basically having nodes that are down. What we did is we started integrating multiple solutions together, and what it provided us is a KVM, a keyboard video mouse, to each and every Mac that we are running in our environment, which is great because then whatever happens, you can still interact with your Mac minis. And also, whatever happens, let's say a kernel crash occurs, or a Mac mini just for some reason decides to hang, you can have power management through smart PDUs like we do, and that can power cycle things. And you can see it from you can see it from this so far that automated provisioning can be hard. You can use multiple solutions, MDM and others, but you more likely than not will need to do some kind of VNC, and you have multiple bad choices. This is a choose your poison and optimize it and try to solve problems situation. Yeah, you need R&D. That's the spoiler I can say here. But for M2, given that this is a known form factor and an old form factor, we were using off-the-shelf components. But M4 landed, and this is a new Mac Mini form factor after 14 years. And after 14 years, if you had the same form factor and new one dropped, the market is not going to know what to do with it and will be very slow to react. So hello, sheet metal manufacturing. You have to start over. Your competitor also has to start over. So you can get a head start if you are willing to risk a little bit and go and design something in-house. So we went ahead and we got higher density than previously, and also we have higher density than anyone, so that's pretty good. We also went and made some pretty nice cooling solution for this uh, because cooling is a bit funky with Mac Minis. Uh, I cannot get into that. That is the shaft design is patent, or there is the patent pending, so I cannot say everything. It also has better cabling. Given that we had an earlier deployment, we learned a lot. If you think about Mac Minis, think how many cables are plugged into a device that you have on your desk and multiply it by 2, and that's how many cables we had. And that gets into the multiple kilograms of copper very fast, and then it gets mind-boggling. So we improved all of that, and yeah, starting over is hard, but also very rewarding because we have a very nice solution. But also we have to ship that solution because we manufactured in Europe. As anybody can tell, my English is not the generic American English. We manufactured things in Europe and we shipped it to the US. That's proven to be a very interesting problem that I have never faced. Shipping software is super easy, but shipping multiple units and many units of rack mount hardware is not that simple. You will need a third party, that's for sure, or anybody will need a third party for that. Uh, as I mentioned, we have Linux and Mac OS, but we don't have everything separately because it's a single team that's handling this. We have a ton and ton of shared automation, and here what we use is copious amounts of Ansible. You can make multiple architecture, multiple OS and whatnot. Ansible for Linux as well. Imagine the same, but with a bit more ifs and a bit more edge cases with macOS and Linux both being supported. Also, we use central controllers to run these automations. So that is pretty nice. I recommend that to everyone. Yes, you can run Ansible from your laptop, but it's not a good idea if you're scaling things. Lastly, you ain't gonna need it. Mantra from software engineering is not gonna work here. You are going to need it. You will ruthlessly optimize, as I said, and that's great, but there are things that you should not optimize out. That is error margins and having some headroom for errors, because you might procure hardware today that's going to arrive 2 months from now, and then it will be deployed another month later, and you will have twice the users. So you will have to think ahead, obviously, how you expand, but also when you are ordering things, think ahead to, I don't know, 1.1x scaling as well, that have a little bit of headroom for maintenance, a little bit of mess ups and logistical issues. And very important, and let me repeat that, hardware is not software. You can't roll it back easily. You might have everything that's every software, every configuration, source code managed, and you can have very nice automations. But with hardware, there are lead times and there is physical movement of hardware. And thank you everyone for listening. If you have any questions regarding this, feel free to ask your questions in Slido. I'm gonna hand over the screen share to the other Peter.
Thank you. And if you stopped sharing, which I don't see, I will share my screen.
I did.
Okay. Okay, now you should see my screen. So as the other Peter already introduced, now we have a data center, and now we have network and machines within. And we would like to utilize those machines the best and the most economic way we can. And that means we want to run a lot of VMs on top of these machines. And yeah, so we will be talking about virtualization for now. So when it comes to virtualization, the question is frequently is whether to buy, build, or fork. And when we initially started to work on the second generation of our build infrastructure, we were paying for a virtualization provider, but we felt that it wasn't really sustainable on the long run because as we scale and as you will scale, so will your expenses as well. So there are a few other points to consider when you are thinking about buying. For example, there is only a certain amount of integrability you can achieve with third-party virtualization providers. Most of them aren't really flexible, and most of them are concentrating on a single operating system or a single architecture. And it would be favorable for us to be able to use a single interface, no matter which build environment or execution environment we are running our software in. And one critical point is that your virtualization is the heart of the CI. So it's mission critical. And when the house is burning, you probably don't want to wait for third-party support to help you debug. So with all this in mind, we decided to bring the virtualization development in-house. And our goal was to create a thin layer and a single interface across operating systems. And we wanted to do it in a way that we can just plug and play hypervisors under. So as it was mentioned, our main focus is macOS and Linux. So we looked at this space for hypervisors. And on Linux, the choice was easy. So there is KVM. It's integrated into the Linux kernel, and it's battle tested. It has extensive documentation. So it was an easy choice. But for macOS, it gets a bit messier. There are a few virtualization providers. There are some paid products. There are some open source products. For example, Dart with a fair use license. But none of them really fit our use case and scale. So we decided to develop our own hypervisor. It's built on virtualization framework, as most of the other providers as well. And as our software matures, we are shifting towards more lower level concepts. But that's how we do it today. So after some iterations, we arrived at a virtualization suite we are pretty happy with today. And in the next slides, I would like to walk you through our first naive implementation and show you why it was lacking, show you some errors we experienced, and then I will showcase where we are at today. And here you can see a pretty colorful piece of spaghetti. In the middle with purple, you can see the different components of the virtualization suite. There is a CLI which interacts with the hypervisor, and the hypervisor runs the VMs, and the VMs has a guest agent running in them. In red, you can see the operating system resources which are assigned for the different virtual machines. These resources can be IP table, rules, or files on the disk, or network interfaces. And in pink, we have different services which run in the same host as the virtualization suite itself. And these services has their own agenda. So like the scheduler agent most probably want to boot new VMs. The builder agent probably want to create new VMs. And the distributor agent probably wants to read VM data or run or get a list of running VMs, for example. So as you can see in this drawing, there is no well-defined boundary in what the different services do. And that was a problem for us because as there are multiple services have their own agenda, they all try to interact with the VMs in one way or another. They were stepping at each other's toes. And one thing to mention here, that is in the first iteration, we didn't have a state for the VMs, just files on the disk. So it was pretty hard to tell whether a VM is actually in a running state or stopping or being created. And that's why we stuffed our services with this garbage collector loop, this GC, that you can see here. And these loops are basically did like cleanup jobs. Like, you know, when you are deleting files, sometimes there are errors, file IO errors, kernel errors. You cannot shield against everything. And there can be leftover files after you delete a VM. That's why we created these loops, which were, again, deleting files on demand, and they were introducing race conditions, stepping at each other's toes. So here you can see the same problem with a different visualization. In the middle, in purple, you can see VM resources, which are files in the disk, and you can see the services continuously and simultaneously writing and reading and interacting with those files, which introduce race conditions. And in our early implementations, we tried to fix race conditions with introducing file locking, which actually did solve some of our problems, but introduced very serious race conditions. No, not race conditions, but performance regressions. And so we thought that we should step back and think, and we can do something better, which we did. And this was, well, this is the latest architecture we have for VMs. And it was many, many iterations, but as you can see, we arrived at an architecture when we have a new component, which is the daemon. And the daemon basically is a in-memory representation of a VM's state. So now we can follow the whole VM lifecycle. And this state can easily be dumped on a disk if we want. And we can rebuild the in-memory representation from the disk as well easily. So you can just kill the daemon, it won't affect the running VMs, and it will rebuild its state when it restarts. And as you can see, now the daemon has the exclusive and serialized right to interact with OS resources, which are assigned to VMs. So now the other services cannot really touch those files, only the daemon can touch those files. And we moved our garbage collector loop into the daemon as well. So now anything you want to do with the VMs happens through the daemon only, and everything is declarative. So these services can request stuff from the daemon. The scheduler can say, "Hey, daemon, please start a new VM for me," and again, a builder agent can say, "Hey, daemon, please create a new VM for me," and the daemon will eventually converge to that desired state. And this architecture gave us fault tolerance. It gave us, or it eliminated the file locking completely. It ended most of our race conditions, and it greatly increased observability, because now we can easily replay VM's lifecycle if we want to debug or something. And as you can see, we have a very clear boundary between the different components. Yeah, we have clear boundaries, and every component has a responsibility to attend to, and they don't step on each other's toes. And believe it or not, we 2x'd our VM management performance. So the whole thing became much more snappier than before. So we are quite happy with it. Again, it's the same problem, but with a different visualization. So now every interaction happens through the virtualization CLI and the daemon. Okay, so now we have a way to run VMs, and it would be great if we could build them, right? So in the next section, I will quickly tell you on a high level how we do this, how we produce our VM artifacts, and I will show you an architecture, and most importantly, I will tell you what happens after a VM is produced. So what customers want from a CI provider is mostly to receive the new tools and security updates as soon as possible. And for any CI providers, for that, we need a fully integrated deployment pipeline. And it has a few building blocks, and I will showcase the most important parts. At Bitrise, we pride ourselves that we are able to release a new, for example, new Xcode comes out, and we are able to release the new stack to the customers within 24 hours. And that means for to be able to do this, we need reproducible builds, like from commit hash. So we need to be able to reproduce any builds we want to. And we want incremental builds to be able to save time and save disk space. So if you have incremental builds, you don't have to rebuild every VM from scratch, because as you can imagine, a VM build can take hours. And if you just only want to update some dependencies, then you should have incremental builds and save time. And you probably want to use the OS in smart ways. For example, we utilize copy on write file systems. So again, we can save expensive disk space by these little tricks. And what you probably also want to do is have nightly builds, because it's really convenient that while you sleep, a new image from the latest tooling gets built during the night. And you can do automated static checks, like checking if the tool versions are really installed what you expected. And you can do performance regressions tests to see if, for example, a new guest operating system version introduces any regressions for you. And of course, you can, during the night, you can run real-life workloads on your freshly built VMs, for example, Firefox iOS, or, I don't know, Kubernetes build. And with that, in the morning, you can have a nice report And if everything's green, you can just click publish, and your users have the new stack. And one more thing you would like to do is save every VM image that has been published to a storage for compliance. You probably want to keep those images for years because auditors can come anytime, and you have to shield yourself. And when you're building your own image build pipeline, you don't want to reinvent the wheel. You probably want to use standard tools where you can. So with all these requirements, we actually give a lot of thought to this and came up with an architecture I want to show you. And what you can see here, and what's the most important, is that we have dedicated builder nodes. And these builder nodes run something called an image builder agent, which basically waits for tasks. And the task just describes what we want to build, like for example, the guest operating system version, the tools, the Xcode version, Android emulator versions we want to include within the image. So as soon as the task comes in, we have this operating system and architecture independent build agent, which is capable to produce different type of artifacts. Like it can produce Docker images, it can produce daemons. It's pretty cool because it has a single interface. You can see this pattern again. And when the image is actually created, I think it's not important how it's created, because it's different for you and it's different for everyone. It depends on the hypervisor you are building against. But as I mentioned, you can choose standard tooling like Packer or Ansible. It actually helps you to create idempotent builds, and most probably your hypervisor is already integrated with these tools. Or if you're building container, you can use the Docker tool set. So it's not important how you do it. What's important is what you do once you have the build artifact. And what we do is basically depending on the artifact itself, we either push it to a container registry or either store it in an artifact storage, which can be basically an object storage or a bucket or any trusted place you have. It's a cold storage most probably. And we have two interesting concepts here. One is the control plane. The control plane is basically, for us, it's a GitOps repository, which has a declarative configuration of basically a snapshot of our system declared the way we want to see it work. And if it's updated, this GitOps repository, it's updated, then the whole system will eventually converge into that state we would like to see. And but it can be a database or basically anything you want to pick. The most important stuff is when an artifact is created, we create an entry in the control plane saying that, hey, this is our new VM version, do something with it. And we also push the new artifact to a so-called supernode. And for now, imagine the supernode as a seed server. And again, the most important part of your image building pipeline is how much do you want to integrate it into your existing system, and what tools you choose. You want to standardize, and you want to integrate it very well, because with tight integration, you can achieve high level of automation, and that gives you speed and confidence. So that being said, we are given a new problem. We have multiple data centers. We have multiple hosts, and these hosts are really different. They can be Linux machines, they can be Mac OS, Mac Minis. They can have totally different disk size, file system, operating system. And what we would like to do is get a set of VM images, which I will refer to as stacks from now on. So we want to get a set of stacks onto a set of these hosts. And I will refer to a set of hosts as pools, like machine pools from now on. So again, your problem is to get a few stacks to a few of the few pools. And it would be really good if we could shift capacity based on customer usage. So it would happen automatically. And by doing this, you probably don't want to overload the network, and you definitely don't want to cause trouble for customer builds, because you can easily create a noisy neighbor effect and disrupt the running builds. And furthermore, you want to be sure that the stack that you have distributed to across all the DCs and across nodes is exactly the same on each and every host, and it's exactly the same as we saved for compliance purposes. So this whole thing, this whole requirement is pretty easy when you have like 10 or 50 nodes. And you can just probably pull the new image from an OCI compatible registry, or fire up a HTTP proxy, or just download from a bucket to every node. But as you scale and as you have 100 or 1,000 or even more nodes, it won't scale. And you have to find a new solution which scales with your size. And if you think about this problem, these requirements probably resemble something, and I believe I spoiled a bit when I was mentioning seed servers. So as it turns out, the BitTorrent protocol can easily solve a lot of problems for us. And let me show you what we have. And this overview is basically showcases everything we have mentioned until this point. So we have a control plane, a central control plane. We have multiple data centers. In the data centers, we have multiple subnets. And at the edge of every data center network, we have virtual firewalls. Some of those data centers are connected either through a VPN, or if you have a lot of money, you can get fancier. And in the subnets, in the DCs, we have these supernodes, which are just very beefy seed servers, basically. And they have a leg in every subnet. So basically, a supernode can see every other host within a data center. And the worker nodes are organized into pools, as I was mentioning. And we have another concept here, which is a super secure DC or private environment, where we don't have superhost because this environment is network segmented, and it's not interconnected with any other data centers or any other customer or public workloads. It's a special case. I will talk about it a bit later. So let me tell you an example. As I was sharing 2 slides ago, when we finish building an image, we publish it to an artifact store, and we do an entry on the control plane. So let's just say that the new Xcode 26 version came out, and developers want to have that within 24 hours. So our builder nodes just finished building the image. An entry was made in the control plane that, hey, the supernodes have this image, do something with it. And one missing piece is that we have an agent running on every node within the DC. So we have something called the image distribution agent, which is again just basically a loop which has a little bit different responsibility depending on where it runs. But on the builder nodes, it has the responsibility to upload and to generate a torrent file, update the tracker, and create an entry in the control plane. And every other node, the agent is actually checking the configuration from the control plane. And if the new entry appears in the pool configuration saying that we would like to get this new stack to the supernodes, actually the agent will download a torrent file and it starts to look for the chunks. And as I was mentioning, the supernodes can see every node in the DC. So it will find the chunks on the builder nodes and it will start to download the chunks. And it will be super fast. We can easily saturate the network within the DC if we want to. As they are in the same subnet and it's happening over a local network, the stack will be distributed to the supernodes from the builder nodes within minutes. And in the same time, the agent on the hosts or supernodes on the DC2 also started to look for the new stack chunks. And as the DCs are interconnected and the agents are paired, it will find the chunks on the DC1 supernode, and it will start to download to this DC. So eventually, the new stack will replicated across DCs. And when we have that, and we have the new Xcode 26 version stack across every DC, we can just go to the control plane, find the configuration for the demo pool, and update the configuration, add this new stack to the pool configuration, and the agents working for the demo pool will actually start to look for the chunks, and they will find the chunks on the DC2 supernode. And again, the download will be happening under minutes. And one thing to consider here is that the agent doesn't have to know anything about the network at all. All network-related stuff is handled by the BitTorrent protocol. And also in the private environment, we have something called a webseed proxy, which is again a torrent concept. We can assign an upstream, which in this case, let it be a bucket. And the agent running on the worker nodes in the secure DC doesn't have to know anything about webseed and proxies. It just sees a new peer, it sees the chunks, and it will eventually download the new stack. And when the new stack is downloaded, there is a hash check. And this way we are made sure that we have the same stack across every node across the data centers. And as I said, we can easily saturate the network within the data centers, which is not good if a customer build is running anywhere. So what we do is basically the agent is capable of detecting if there is a customer build is running. And in that case, we either throttle the network download on that host or we pause the download so we don't mess up customer builds. And yeah, I wanted to tell you about a bit about the algorithm of how do we assign stacks to hosts, but I'm running out of time, so I think I will just hand the mic to Sabi, and maybe we can get back to this during the question Q&A. So I will stop screen sharing.
Thank you, Petty. And I'm sharing again, right? Cool. So the next layer when we are building this platform is called central instance management. We love control planes everywhere. And what we are trying to solve here is being able to really easily create a virtual machine across all of the fleet that we have from all of the hosts, regardless of its size. Because if you want to create a virtual machine, you have to find a host that has the sufficient amount of CPU, RAM, disk, whatever. Plus, it also has the virtual machine image present on it, because you cannot really distribute all of the images everywhere if you're using local disks. And we do not want to go to each individual infrastructure host and manage VMs there one by one. We just want a nice central control plane that we can ask that, hey, give me a virtual machine of this spec, and it will do it for you automatically. So how we did it is we picked an open source solution called Nomad. It's pretty similar to Kubernetes, but it's a lot simpler to both provision, operate, and make modifications to. It has two main components. One of them is the Nomad server. You usually deploy it somewhere as a cluster of nodes, and this is the API plus UI plus whatever that you can issue your instances from or list whatever is running or stop running once. So this is the server component. And then you have Nomad clients. Those are running on each and every infra host. And this is the component that connects the infrastructure host to the Nomad server. So whenever you issue a new VM from the Nomad server, it will figure out which Nomad client can do that, which one of them has sufficient resources and all the constraints checked. And then the Nomad client is responsible to handle all of this locally. To do so, Nomad provides you a bunch of different drivers out of the box. But as we have our own, called the Bitvirt CLI that Patty talked about at the virtualization level, we need the new driver. We have a single driver that works with both macOS and Linux machines, as the Bitrise CLI has the same exact interface across the two. So we can just cross-compile the driver to both macOS and Linux and distribute it everywhere, and it just works. And this is actually all that we started off with a few years ago. But Nomad server has some problems that we run into. Firstly, if you issue a lot of list commands to a Nomad server, then you will really quickly overload it. And yeah, it will just die on you and you won't be able to use it. For that, it provides an event stream that you can attach to, and you don't need a full list command every time to check what is the current state of the system. It will send you incremental updates from the event stream, but this event stream unfortunately doesn't guarantee anything. It doesn't guarantee at least one or at most ones delivery. It's just ad hoc, and as the load on the Nomad server increases, you will most likely experience some loss in the messages, in the updates. So we created an event collector that is attached to the event stream of the Nomad server. It tries to incrementally update the current state of the system into a data source, so materializing the events. And in case it missed some, it will do a periodic full reload, so list call every 5 minutes or so. So if we missed an event that this VM was created or deleted or whatnot, then on the list call, we will definitely see it. And this way we will both eventually get to the same state in the data store, that is the current state of the system, without overloading it. We just put an API on top of the data store, and all the other systems like the pre-booting system, which I will talk about in a minute, can use that. So Nomad is 100% encapsulated inside the instance management system. We have some thin components around it, and we expose usual gRPC API that we always do from the instance management system's point of view. The next one is observability. This is actually where we spent most of our time in the past couple of years, because we wanted the best possible customer experience in terms of stability and performance. And of course, we do have a bunch of different metrics and traces and logs. And on top of these, we do have alerts, and we do have on-call rotations for the different teams. I'm not going to dig deep into these, because these are pretty usual ones at every company. I will talk a little bit more about what might not be present at every company. First off, just using these things that I just described, we have a bird's eye view dashboard. Using the bird's eye view dashboard, you can look at all of these systems and the resulting customer experience from a really high level point of view. And on top of this huge dashboard, we have so-called customer-facing service level indicators and their objectives. These are things that customers will actually, so users of the system will actually experience directly. Like if the build queue is super long and you have to wait a lot for your builds to be started, then we will have that on the customer-facing service level objectives. If the virtual machine image is really out of date, it was built like 3 months ago or something, then you are probably missing out on some tooling updates, then certificates on the VM image might get out of date, etc. So we don't want that. We want fresh images with security updates and all of that for you really, really frequently. And we will see the image ages at this section as well. Then we have other sections per system. When I say per system, I pretty much mean what is on the left side of the presentation, a bit more. And we identified the most important indicators per system, defined an objective, we measure it there. And of course, that's not all of the measurements we have from these systems, because you cannot put everything from all of the systems onto a single dashboard. So the secondary purpose of the bird's eye view dashboard is to be a catalog to lower level, more detailed dashboards. So if I do see that a high level indicator for image distribution is going red, then I can really easily zoom into it from this. And this is not all of the data that we collect. You can, of course, collect almost anything in metrics, traces, and logs combined. But if you do so, you will most probably have really high cardinality data, which is really hard to store for yourself on-prem. Or if you are paying for a managed solution, then you are going to pay a lot, because usually, especially for metrics, they usually price by the degree of cardinality that you have in your data, because the higher cardinality the data is, the higher or the bigger index that you have to build for that, and keeping that in memory and whatnot is really challenging. So we also publish a bunch of events. We store them in SQLite database, and we have a bunch of metabase dashboards, so we can zoom into more detailed data in there that we didn't or couldn't want to store as the previous ones. Another, I think, interesting thing that we have is called continuous testing framework. The challenge that we faced was that we really wanted to measure how the build duration, so the CI builds duration, changes on our system, as well as their success rate. We wanted to see if we release the new VM image, let's say Xcode got slower, faster, less stable, more stable, whatnot. We wanted to see that. And it's really hard to get from customer data, because they are changing the way they work with the app. They are going to change their tests. Tests are going to fail. If you measure that, then you are not actually measuring if the new VM image got slower or faster or flakier or whatnot. You are measuring how that customer is interacting with their code base. So we created some so-called reference apps. These are applications that are similar to our core customer base uses. We pinned it down to a specific commit. We are not changing anything, only if it changes on a new export version, or whatever version, we are making it compatible. But generally, we are not touching that reference app. And all we do is we have a cron-like expression in the same declarative GitOps configuration that Patty and I also talked about in the chat. And we define on what stacks we want to run it on. So in this example, this Linux stack, and what machine types, and the system continuous testing framework will continuously automatically run this for us, also measuring everything that we are interested in. So we can be sure that we didn't change the input of the system, the build. It's exactly the same build request. So if anything changes on the output part, build duration, success rate, whatnot, then we can be sure that it's our system that produced this change, not the input. The last thing that I wanted to show you on the observability part is called build analytics, build virtual machine analytics. So we are collecting build logs and build VM logs from everywhere, and we are automatically looking into it, collecting analytics. And in the same GitOps repository, we are defining things that we want to automatically look into when we receive a log. So if in the logs we do see that failure unable to connect to VPN, it's an exact match in the logs, then we are raising this unable to connect to VPN error. We indicate that this is a bug somewhere and it's assigned to the build infra team. And we have a bunch of others, both with exact matches and regexes. And from those, you can look into patterns here because some of them are expected to happen, but if there's an increasing trend, it's a problem. Some of them are not expected to happen at all. For those, we kind of have like an incident situation where we immediately jump into it and try to fix it. So it's a really nice looking glass into what is actually happening across a large number of builds and build VMs. We actually looked into not using exact matches and regexes and whatnot, but AI-based technologies. But it was not working as well as a simple grep. So we kind of just fall back to grep at the moment. But we will try to experiment with AI-based technologies still. They were pretty slow to your use case, pricey, and deploying it locally, keeping it inside Bitrise territory is also a challenge on its own. And it also gave us some varied results. Like sometimes it was surprisingly good, and sometimes it was full of false positives. Okay, so now we theoretically built the platform together as part of this presentation. And on top of this platform, we are going to put one point solution, one use case, which is CI. So how the CI works is, as a user, you trigger a build request, it gets enqueued to a queue, and you have some workers who are also looking into the same queue, and they are dequeuing your build request and execute it if they can. And we are not creating the workers when you have already placed your build request into the queue. We are rebooting the workers for you. So they're already sitting there, 100% warmed up, ready to execute it. So when you fire a build request, you trigger a build request, it will immediately be picked up. So you won't need to wait for 10 to 20 seconds for a build VM to start. It will be instant and it will start in a few seconds usually. To do that, we have a so-called reconciler component. It's the same stuff that Kubernetes has, for example, internally to converge the system to the desired state. And we do that. We give a desired number of prebuted VMs to the reconciler per pool, meaning VM image plus machine type, because you need that information to create a virtual machine. And it looks into the current number of prebuted VMs from the same pool. And if there is a difference, if you have fewer prebutes than you need, then it will create some new workers for you. Workers are basically, it's a component running inside the build VM that is capable of dequeuing and executing your task. And if you have more prebutes than you should have, then it will downscale it. This is pretty much what the reconciler is. And the input for the reconciler, the desired number of prebutes, is the output of an autoscaler component that automatically figures out which pool needs what number of prebutes. I will zoom into autoscaler and queue now. The reconciler is just that, so I don't have a slide on that, but if you have any questions, then don't hesitate to ask it, please. The first component that I want to zoom into is the queue, how the queuing logic works. So on the build request part, you have some requirements, and on the worker part, you have some capabilities. And the build request here in this example stated that it needs Xcode 16.2 and for Pro Large public cloud to be executed. And worker 2 doesn't have any of these as capabilities. It can execute some stuff, but not this, completely different things, Linux Android thing is. And worker 1 has these capabilities plus a little bit more. which is fine because it's capable of more than what we require. But we can actually accept this build request and execute it. It would also be able to execute different minor versions of Xcode builds because all of them are installed on the same VM image. But we don't need all of these capabilities to execute this build request. So we give it to the worker one, and it will run your build. The other component is the autoscaler in this system. This is a really high-level idea on how it works. I won't go really into details, and yeah, no worries if you cannot really read this. I just wanted to give you the basic idea, which is we observed a weekly trend in customer usage. So if we saw that last week, Wednesday, 5 p.m. was the peak hours of system usage, so customers using the system, then it's very, very likely that this week, Wednesday, 5 p.m. will again be the peak hour. And you can see the same trend every week. And what we do as autoscaler, we are somewhere here in point in time. And we are trying to figure out per pool, so per VM image plus machine type, what is the trend between the 2 weeks, because if many customers migrated from one Xcode version to another Xcode version, then there is usually a trend in change between the weeks. And we try to figure out this trend multiplier by looking into the last, let's say, 30 minutes now, and the same exact 30 minutes but a week earlier. And if the trend is 1, that means that there is no change. We should expect the same number of builds coming in this week that we have seen the previous week. If the trend is, in this case, 2, that means that we will most likely have 2 times more builds coming in at given intervals this week compared to the same given interval last week. And this is how we try to predict the next 10-15 minutes. And when we can predict the next 10-15 minutes, then we can calculate the desired number of prebuilds, and we can give that information to the reconciler, and the reconciler will prebute the VMs accordingly. So whenever you push the button, you will get instant build execution if everything goes well. I wanted to share a few other point solutions and why building a really nice execution, a build platform, a Bitrise platform, whatever call it. So these black and green blocks here is nice. It's because you cannot only run CI on top of it, you can run a bunch more. We already have 2 other use cases or point solutions generally available. They are related. It's called build cache and RBE, remote build execution. If you are familiar with Bazel, Twist, and similar technologies, then this is pretty much it. The build cache enables you to store compilation results, test results, whatnot results. So whenever you are re-executing the same exact test or compilation or something, either locally or in a CI build, then you don't have to do that. You can go to the build cache and fetch the results from there and save some time. If you still need to execute it because it's not in the build cache, then RB comes into the picture. It's remote execution, which enables you to execute the command, the test command, the compilation, the whatever command, remotely, not on your local machine, but in a remote build execution environment. And we use the same exact virtual machines that we talked about for both CI and RBE, same images, same tooling, same observability, same everything. And the build cache is also sitting on top of the same architecture. All of this on the same switch fabric, meaning it doesn't go out to the internet to access these. So the connection between them stays local inside the data center. And this way it can be as cheap as possible for you, as performant and as stable. Other 2 things that I wanted to mention are still under development. One of them is Codespaces. It's very similar to GitHub Codespaces. It's remote developer environments, which is really close to what we are already doing. We have a bunch of VMs, we have a bunch of toolings installed, we have central management and everything. And we could fire off these to provide remote developer environments. So all of the things pre-installed are available to you automatically. You don't have to do all of that on your local machine. Both JetBrains based and VS Code based editors already provide a lot of support for this. So if you provide the infra then or in the platform, then they will usually solve the rest. And our latest development that we are working on right now with focus is AI agents. There are some solutions out there already that enable you to kick off AI agents on remote machines, not on your local machine. And there, usually, they don't have a bunch of different execution environments. They mostly only have Linux. And there aren't that many tools pre-installed. You usually have to do it yourself as part of the startup process. We are planning to provide a similar experience to them, but also providing macOS and a bunch of tools pre-installed and all of these. So what I wanted to showcase here is that once you have the platform built, you can use it for a lot of different use cases, and a lot of different voice solutions can be built on top, and they can interact with each other in a really nice manner and in a stable, performant, cost-effective manner. If you're interested in any of those new things that we are working on, then please reach out, and we might even be able to collaborate in some ways if you're working on similar things. And thank you.